Hello everyone and welcome to our Splinter meeting. My name is Anastasia Kokori and I am the Public Engagement Officer for the UCL Center for Space Exochemistry Data, and I'm coordinating the collaborations between professional and amateur astronomers for the Ariel space mission. We are very happy to organize this meeting as part of this year's EPSC2020. And EPSC has a long tradition on organizing and hosting sessions dedicated to amateur astronomers. And these sessions really highlight the importance of the work done by amateur astronomers for planetary science and astronomy. There are other events happening during EPSC 2020 dedicated to amateur astronomers. So if you're interested, please check the website for more information. Today's meeting is focused on exoplanets and the contributions by amateur astronomers, and specifically for the Ariel space mission. And actually, this is the first time that such a meeting, Splinter meeting, is organized in an EPSC related to exoplanets and amateur astronomers. So we really hope that this is only the beginning and more such meetings will take place in the future. The agenda includes several topics and presentations by different speakers to cover different aspects of the Ariel space mission and the support from amateur astronomers. We are very delighted also to have the PI of the mission, Giovanna Tinetti, who will be our first presenter. But before we start, just a few notes for the procedures. You have the opportunity to ask questions after each presentation, or just type them and we will respond at the end of the meeting during the roundtable discussion. So your microphones are muted during the meeting, but you can use the chat function. And also, this meeting will be recorded and will be available online if you want to watch it later on or share it with other people, and will be open to everyone. So if we are ready, Giovanna, you can start and share your screen.
Hello, Anastasia. Thank you so much. Should I present my slides?
Of course, yes. Please share your screen.
Okay, good evening to everybody. It's a great pleasure to be here today and meet you virtually, unfortunately not in person. I would like to thank in particular Anastasia for having organized this session. I think it is a fantastic initiative, and I hope we'll have the chance of following this session with many others, in particular in person, not just virtually. So a few words about Ariel. So as you probably know, we have a number of general observatories and dedicated space mission to find exosolar planets being planned, already flying. So it's fair to say that exoplanets are really living in a golden age. A Nobel Prize that was given for the discovery of the first planet around a star different from our sun this year. So clearly exoplanets are a fantastic field of research, both for scientists, but literally, really for everybody. And in this long sequence of new observatories and dedicated mission that will come online, Ariel will be launched in 2029. And so what is the unique selling point of Ariel? Well, Ariel will address a number of questions, but in particular, three main objectives. We want to answer the question, what are exoplanets made of? And in particular, we want to understand what are the physical processes that are shaping the planetary atmosphere, because Ariel will focus on the observation of planetary atmospheres. And we want to use this information to understand more broadly how do planetary systems form and evolve in our galaxy. So clearly it's a very ambitious question. And in particular, if we think about formation and evolution of planets and planetary system of our galaxy, today we have a number of theoretical hypotheses and theories that tell us as how planet should form in our galaxy, but we still have many open questions, in particular because missions like Kepler in particular, but also other facilities are indicated that the most common planets in our galaxy are planets in between the size of the Earth and the size of Neptune. And we call these planets in many different ways, in part to hide our ignorance. In this particular graph that was made by Diego Turini, they're called transitional planets. And these are the most common if we're looking at the statistical information that we are gathering out of the telescope like Kepler. But they don't exist in our own solar system. And so we don't know anything really about these transitional planets. Are they big terrestrial planets, or are they small Neptune? Are they somewhere in between? And clearly we have many questions that we'd like to address. But also when it comes to small planets, terrestrial planets like the Earth, like Venus, we're expecting a huge variety of that. And so we're expecting that not all terrestrial planets will behave like Venus and the Earth, both in terms of composition of the interior, but also in terms of the atmosphere. And so we have all this question that we really want to try to answer. The study of the atmosphere, in particular the chemistry and the structure of the atmosphere of these planets, will help us understanding many of these questions, because we believe that the chemistry in particular, so the molecule that are and atoms and ions that are present in an atmosphere, can be used in a certain sense as a tracer of the history of these planets. And so if we're able to look at not just a few, but a large sample, large population of planets in our galaxy around other stars, and if we're able to probe the chemistry of all this atmosphere, we will be able basically to address a lot of open questions that today we cannot really answer. So what is Ariel exactly? Ariel was selected by the European Space Agency in March 2018 to be the next medium-sized mission to be launched by ESA. The launch is planned in 2029. And we're talking about a 1-meter telescope able to do spectroscopy from the optical down to the infrared simultaneously. And the unique selling point of Ariel is the ability to do this for a large population of objects. We're talking about roughly about 1,000 exosolar planets for which this observation will be obtained. And this needs to be compared to what are the current observation of exoplanet atmospheres that are typically just for a few tenths, and for which we know very little actually. These observations are not optimal. And so in this 1,000 exoplanets sample, we want to be able to include both rocky planets, but also gaseous one, with temperature from the 300 to 3,000 Kelvin, so really a huge variety of cases around a different type of stars. The Ariel Payload Consortium includes the contribution of 17 ESA countries, plus a contribution from NASA that has been approved this year. Ariel will be launching L2, this very stable point at 1.5 million kilometers away from the Earth, together with Comet Interceptor. So we will share a launch by Ariane 6.2. And from that point, from L2, we'll be able to, we have the vision of the sky that you see on your right, where basically we'll be able to cover throughout the year the entire sky. But the instantaneous field of view is about 40% if you're close to the ecliptic. And on the contrary, we have 100 instantaneous field of view towards the galactic poles. What you see in this colorful dot that you're seeing here are existing planets that we know that are already optimal targets that could be observed by Ariel. And the black dots, on the contrary, are the test objects of interest that in principle, if confirmed, would be optimal targets for Ariel. So I mentioned that the Ariel consortium is including a contribution of 17 ESA countries. And so as you can see in this diagram, part of the hardware is being delivered by many institutes and industries in all these countries. You see what is a view of what Ariel should look like when it will be launched. So I mentioned that Ariel will do spectroscopic measurements, and so in particular, Ariel will cover between 0.5 micron in the optical down to 7.8 micron in the infrared simultaneously, so in one shot. And this is very important because, as we already know, stars are sometimes a bit active, and so we want to be able to do the measurements all together in order to avoid any potential contamination due to the stellar variability. But also we want to cover this large wavelength range for a number of reasons. I'm mentioning just a couple of those reasons. We want to be able to probe as many molecules as possible in these atmospheres, and you have a sample here in the diagram on your right. Most molecules have a very strong signature, in particular in the infrared. And so that's why we want to be able to cover this infrared part of the spectrum. And that's why also we need to be in space, because of course these wavelengths are very hard to be measured from the ground because of the telluric contamination. But also we want to be able to include the visible wavelengths, because these are extremely useful, for instance, to understand whether there are some clouds and what type of clouds we can find in those atmospheres, also to monitor the stellar activity. And more in general, we want to be able to probe this very broad wavelength range, because we want to be able to look at planets at different temperature that then they are clearly emitting at different wavelengths in the spectral range. Since the discussion today is mainly focused on follow-up programs, I thought that focusing a little bit our discussion on targets and could be useful. And so here you have a plot showing the aerial targets that are already existing today. And so we have a bit more than 500 targets that we know we would like to observe with Ariel. And as you can see, they're already quite diverse in terms of planetary size, so we can cover both small planets but also large planets. So this is certainly good, given that we want to probe a relatively diverse parameter space. And also if we're looking at the temperature, as you can see here, we can probe objects that are temperate up to objects that are definitely very, very hot. Now, if we're looking at the stellar brightness, of course, the interest of Ariel is to focus as much as possible on planets around extremely bright stars, because it means that we can see more photons, and so we can have a much better measurements, a much more precise detail of those atmospheres. And so at the moment, of course, the current sample is still biased towards stars that are bright but not so bright, and so typically they are, the average is on stars that are brighter than a K magnitude equal 11. But clearly, even just the TESS object of interest, they're already much brighter. And so clearly TESS is providing new and even brighter targets, which are absolutely fantastic for the purpose of Ariel. Clearly, between now and 2029, we will have the opportunity of collecting many more planets and to consider them for observations because of TESS, of course, but also other facilities like EOPS that has already published the very first result, which is wonderful, and Plato that will be launched in 2026, and many other facilities from the ground. So clearly, we are relying on all these facilities to deliver more and even more interesting planets that Ariel can study. And so what you're looking at here are the predictions, even just based on TESS deliveries. And so out of the roughly 2,000 optimal planets that we expect to be in there in 2029, Ariel will roughly select half of them, about 1,000, for our observations. And again, as you can see here, we'll have a lot of choice in terms of parameter space that we can probe. So we are confident that we'll have a very long list of planets to select from. In order to be very efficient, we are already worked on a 4-tier approach, where we have, first of all, like a reconnaissance survey, where we're looking at 1,000 planets, not too much into detail, but we want to have a quick overview of how these planets and this atmosphere might look like. And out of those 1,000, we will select half of them for very detailed and full characterization of the atmosphere, really asking very detailed and precise questions. And then we want to select between 50 and 100 targets, what we call benchmark. These are really great planets, typically around extremely bright sources. And the idea is that we want to keep observing them through time to study weather, variability in those atmospheres that we're expecting, being planets. And so this will be basically our guidelines also to interpret the other planets that we might observe less frequently. For a number of those planets, we will also follow them, not just when the planet is transiting or is going behind the star during the eclipse, but we want to follow them throughout the orbit and measure what we call phase curves. So really how the planet is changing as a function of phase. And these are great observations because they tell us something about the three-dimensional characteristics of the planet, not just one particular snapshot. So clearly phase curve will be really great to deliver even more information.
It's cutting off the sound in a moment.
So the mission lifetime is 4 years with the possibility to extend it to 6 years. And we already have a plan of how many planets roughly we want to observe as tier 1 or tier 2 and tier 3. Of course, this plan is expected to change, not just because of the new targets and the area consortium work, but also through interaction with really all the community. And so clearly amateur will have the chance really of shaping the mission and really suggesting where should we focus. So it's not really just something that will be decided by a small team of people. It's really something for which we need absolutely input from the broader community. Of course, Ariel will not operate in isolation. We'll have other facilities that will operate either in the meantime or before. And in particular, we're already planning many synergies with the James Webb, but also with Hubble. And clearly James Webb will be quite unique when you want to probe atmospheres of small planets, in particular around a very cold star. But when it comes to bright sources and in particular hot and warm planets, then the characteristic of JWST and Ariel will be very similar. And so clearly Ariel will offer the opportunity of going to the characterization of a large sample of planets, whereas probably JWST will offer fantastic opportunity in more in a smaller number of individual objects. Of course, we want to also consider many synergies from the ground, because clearly large facilities like the Extremely Large Telescope and our similar facilities will probably operate in 2029. And from the ground, what you can do is to deliver spectra at extremely high resolution, which is wonderful to pin down and nail down some very weak absorption features that from space are hard to capture. But typically they are focusing on a much more narrow wavelength range because of course from the ground you cannot have access to the broad wavelength range that Ariel will deliver from space. So being able to combine ground-based facilities and Ariel will be absolutely fantastic because they will be extremely complementary. In January 2020, before all the COVID situation started, we had a great opportunity to be able to organize an open conference in ESTEC, and there were more than 200 participants from 19 countries. it was absolutely wonderful to hear the feedback of the community for the work we've done so far. So that was a great success. And I put here this picture because I really hope that we'll be able to do even more open conference very soon in person, because although these virtual meetings are very useful and great, so they cannot really substitute, at least in my opinion, in-person meetings. And so hopefully I will be able to meet you all very soon somewhere in Europe. So I'm very grateful to Anastasia, her colleagues, for the fantastic work they've done with ExoClock. And I will not dwell more on this because I know it will be part of the discussion done today. But this slide is really just to say that this is a fantastic work and is absolutely critical for the success of the mission. And so let me wrap up to conclusions here. We have learned very recently in the past 20 years that exoplanets are really ubiquitous in our galaxy. We have found them around every type of stars, and we're expecting them to be even more numerous than stars in the galaxy, which is absolutely brilliant. And this number of discovered planets is increasing exponentially, which again is fantastic, but we still know very little about them. And so Ariel is about to really try to understand more the nature of this planet, what they're made of, how they form, how they evolve. And so to do that, the idea is really to deliver the first chemical survey, let me call it that way, of about 1,000 exoplanets, and really use this survey to understand all these intricacies that will tell us more about the complexity of this planet, and ultimately why the planets in the solar system are not similar to other planetary systems that we're seeing out there. Precise ephemerides are really essential to maximize the science return of the mission, because again, 1,000 planets and the kind of plan that we have is really very tight, so we cannot lose time in scheduling the measurement of a transit or eclipse and then find out at the very last minute that the transit is not really occurring we were expecting. So that will be a negative impact on the efficiency and the return of the mission. And so we need to make sure that all the information is really there before the mission is flying. So thank you so much again for your participation, your help in making sure this is happening. Once more, if you haven't started to work with us yet, you're absolutely welcome. And I'm sure that Anastasia will tell you everything you need to know in order to join the adventure. Thank you very much.
Thank you so much, Giovanna, for the excellent overview. If you have any questions for Giovanna, so you can either type them in the chat function. There will be some time at the end of the meeting, so you can definitely ask the questions at that point of time. It's always good to have them in the chat area in order to better arrange the queue. So we have, I think, room for one question now. So if there is really one question, we can respond it. So let's see. Otherwise, we can definitely wait for the end. This is fine. Okay. All right. So the next, perfect. Okay, so the next presentation is by Athanasia Nikolaou from Sapienza University, who is also an active member of the Ariel Consortium. So Athanasia will talk from a different perspective, and we are very happy to have her with us too. Athanasia, you can start the presentation when you're ready.
Hi to everyone. Let me share my screen. So have this. So I'm actually very happy that I'm here with you, and talking after Giovanna, I'll try to concentrate on one aspect, right? Because we had the overview we had already. So the idea here is to dive a little bit more into some of the planetary perspectives of Ariel, trying to understand our planet, our system, in relation with the others. Therefore, the analogy with the tree. So yeah, let me start. So generally here, our solar system is going to be the tree, and we're trying to put it in the context of the forest of exoplanets, if we can call it this way. So the statistics of the extrasolar planetary systems that we already have discovered indicate that the default mode of planet formation is different than what we see in our system. And let's see how does this plot. So here is a plot from a paper of 2015. It's a very nice comprehensive survey of the planets found in Kepler in that case. And you can see different planets with different circles. The sizes are for reference also in the bottom. And there is a different color code. The authors chose to put how many planets were found in the host star where each planet belongs. Therefore, we have with green 4 planet systems, with purple 3 planet systems, with red the 2, and the rest, which is the majority, is with blue. So that's single planet systems. Now the question is that an artifact or no? For starters, we can definitely say that we see a difference with respect to our system. So the Mercury orbit is plotted here for reference. You see the gray circle. And the radii are measured in radii of solar radii, our sun. So you see that compared to those systems, our system is lacking a lot of mass in the center, because the systems of exoplanets basically show that a lot of mass is concentrated close to the host star and in orbits much closer to Mercury. So what should we do about this? For the first, we should be open to novel perceptions and to challenge the old ones. And we don't need to go very far to see how we have been forced to reconsider science. And we stay in our solar neighborhood for the case of Pluto, especially. So Pluto was discovered in 1930. And a few decades later, its satellite Charon was discovered. So in that case, the system is binary and the one body orbits around the other. So the barycenter is located outside of Pluto. However, we're still going to refer to it as satellite. And that's how we still refer to it. It's also a bit bigger than Pluto. Another decade later, the trans-Neptunian objects started to be discovered. And then it was a matter of time to discover an object that was similar in size with Pluto. In 2003, that was Eris. And that was a problem then, because the EAU had to reconsider the planet definition, right? So in 2006, it was deemed that Pluto had to be demoted from the status of planet and be a dwarf planet, because it hadn't cleared its orbit around the sun from other objects. And then it took until the New Horizons mission that actually passed around in the vicinity of Pluto to discover that the fact that we demoted Pluto in a dwarf planet didn't make the picture less complex. So it was not low in complexity. The world that was discovered there was found to be much more complex. It had ices, nitrogen and methane ices. I also direct you to the contribution of Holler of this conference. It's very nice and very descriptive. So it actually tells us that we didn't solve the problem of complexity. We found, however, a new category of planets, the dwarf planets, and from there we moved on to understanding our solar system. Therefore, we should keep this mindset for starting small planets in Ariel. And I'm not referring to dwarf planets, because these are not possible to be seen with Ariel, but small planets in the context of Earth-like, terrestrial-like, Mars size, these like rocky planets. Those are the small planets in this talk. Ariel is going to help in that by enabling planet demographic studies, by breaking the composition degeneracies whenever is possible, and by monitoring formation in young populations, because it focuses in hot planets and they are likely to be hot when they're in the growth stage or shortly after it. So firstly, how do the surveys enable the theory testing? That's on the left side, you can see the Fulton gap. So you can see a binary distribution of planets. These are the Kepler planets. And they have been arranged, as Giovanna showed before, in terms of Earth radii, so radius versus occurrence. So it's a histogram. We see a binary distribution. So the apparent gap between the two distributions, super Earths for red and cyan for sub-Neptunes, has not been explained. And there are a lot of theories that try to explain this. One tentative and very recent result, I'm not advocating for this theory, I'm just setting it out there, has been from Berger et al., and that's a Gaia-Kepler survey. So what the authors did there is that they tried to separate the planets in two data sets based on how old their host star is. And why is that? That's because the way that we date the stars is also including some uncertainties. So what they suggested in that case is that the gap could be something that we see shifting according to the age of the clusters that we plot. And so they argued that possibly the sub-Neptune size is something that is going to disappear as the system evolves. Now, how Ariel helps in that? By sampling a larger number of population, it is elaborating the planets in 4 different tiers of resolution. So we will be able to put more constraints in the mass of those systems, in the mass of those planets, and better constrain those results and test theories like this to understand if the gap really exists or what else generates it. Now, second thing, we want to break the composition degeneracies. For those who haven't seen before a ternary diagram, that's a colorful triangle here. I hadn't seen it myself because this is actually very common in mineralogy. But astronomers don't tend to be familiar with this. However, what this shows for someone who sees it the first time is the proportion of a composition among 3 candidates. So the corners of the triangle correspond to different pure compositions. And the closer you are to each corner, the closer you are to the pure composition. Now, why we plot this? This has been plotted by Valencia, a work of Valencia, for the planet GJ1214b. That's about 6 to 5 Earth masses. So this planet can be compatible, or let's say the mean bulk density of this planet corresponds to 2 different compositions in this ternary diagram. Everything on this ternary diagram has the same mass. So it can be either a water interior with a steam atmosphere, or it can be a rocky interior with a diluted hydrogen-helium atmosphere. You can understand that's a completely different alternatives. So what Ariel will try to do is to break the degeneracy when it is possible to probe upper atmosphere to the bar level. And this is possible with technology employed with Ariel. So we're going to try to put a constraint on the atmosphere, therefore ruling out one of the 2. In that case, I ruled out one per chance. This is definitely not a suggestion of how GJ1214b is. But you can understand that the constraints help us to rule out scenarios for the planets. Now, keeping on this aspect of the composition, we're going to stay here. There have been efforts since a long time to constrain the elemental planetary composition. This has brought into dialogue 2 different communities, and one is the astronomers and the other is the mineralogists and geophysicists. And I will let you guess which is which. However, for one of these communities, the metallicity is something completely different than for the other. So this is an official opinion, of course, but this is an anecdote in the community that astronomers consider that metal is anything that is heavier than hydrogen, right? So this has caused basically some flourishing in the dialogue between the 2 communities in the end. So as you see here on the left side, for staying with the astronomer point of view, there has been studies to try to find a correlation between the host star total metallicity and the planet's total metallicity. And as you see here with some recent results, the slope one is ruled out. What does this mean? That there is not a proportion between the 2. A positive slope is not discarded, but the slope one is ruled out in 2 sigma certainty level. So this suggests that we still don't have a way to understand if the host star composition relates to the planets and how does this happen. On the other hand, we have on the right the chemical trends of depletion and the view of a geologist. So geologists tend to, here they have, we have a plot from Wang et al. That's 3 abundances, 3 elemental abundances plotted there. The yellow corresponds to the sun, to the proto-sun. the red corresponds to C chondrites, which is a type of meteorite in our solar system, and the blue is for the Earth. Now, normalizing everything to the abundance of the C chondrites, you can see that the sun is enriched with respect to the red, and the Earth is depleted with respect to the abundance of the red. Therefore, these are the two views. Both try to understand the systems and the generation of planets proportionally to their host star. Ariel is suggesting to aid in this procedure by putting color diagrams, which is a new type of representing data and elemental abundances and ratios. So last but not least is to revisit the models of the planet formation. We need to do that because, as we said, the architecture in our solar system is not very common. So what I want to show here is that we need to be able to reproduce the configuration of the solar system at least, and also other systems, by n-body simulations. And that's another modeling effort that is done since a lot of years. Now, one of the main aspects of this is the role of giant companions. We said we're not going to talk about the small planets, but actually the giant companions play a huge role in their formation. Why? And you can see here on the right side, two reasons why. For our solar system already, there is more than one theories about how we were able to obtain a Mars-sized planet at the time, at the orbit where it is. And there have been suggested two solutions. One is the Jupiter Grand Tack scenario, suggesting that the gas giant of Jupiter migrated inwards from 4 AU to 1 AU and 1 back, and dragged with it all the C-type, so all this blue material, which is the water-rich material, and delivered it inwards. The other suggestion from Isidore et al., this is that there has been chaotic motion in the early system already. So we don't need such a tailored, directed motion of Jupiter to explain that. So that's another open question. And by observing other systems, we will be able, and trying to find their gas giant companions, we will be able to address this better. So therefore, yeah, I leave you here. This is my 12 minutes already. And the idea here is to keep in mind that Ariel is going to try to break the degeneracies of composition wherever this is possible by probing deep in their atmosphere up to the bar level. The second is the population studies that is going to enable by sampling a larger set of exoplanets. And the third one is that we're going to try to observe different configurations of systems. So we have more to enrich our theories. Thank you very much for your attention.
Thank you very much, Athanasia, for the very nice presentation. So we have probably room for one question and then the rest at the end when we have the roundtable discussion. So please, if you have any question for Athanasia, you can type it in the chat function and then we can really ask it at the end. So I don't think we have much time left. All right. If there is no question at the moment, you can always type it in the chat function and we can ask it to Athanasia and the other speakers at the end. So I think we can continue just to keep things going. Thank you so much, Athanasia.
Thank you.
Right, and the next actually talk is mine, so I'm going to share the screen. Okay. Okay, so, all right. So hello again, everyone. For anyone that has just joined or was not in the beginning, my name is Anastasia Kokori, and I am coordinating the ExoClock project, which is dedicated to the Ariel mission. So together with Angelos Tsiaras, we have founded the project, and in this presentation, I will really share the scope of the project, the different aspects, the features that we have developed, and also I will show you step by step in more detail how anyone interested, including amateur astronomers, can join the mission and participate in the project. So we have heard about the Ariel mission, the objectives of the mission, and Ariel will observe thousands of exoplanet transits and eclipses. So these are phenomena that are happening at very specific times. And as you can imagine, it is very important to have accurate planning in order for the mission to work more efficiently. Now, I will show you an example of what this exactly means in practice. So imagine that Ariel goes and observes planet A. So this is perfectly fine, as you see. However, when it goes to observe planet B, it has missed it because the planning was not really accurate. So the prediction was not very good. And that means that we have missed the transit or important information about it. Indeed, most of the targets now have large uncertainties, and the targets that are being discovered now by tests have even more and larger uncertainties. So this is exactly where ground-based telescopes, including small ones and medium-sized, can become important and contribute to the mission. So how? By observing the Ariel targets regularly and before the launch day, which is in 2028. Now, to more efficiently organize this effort, we have initiated the ExoClock Project, which is an effort where we make the best use of resources and at the same time bring together people from different backgrounds. So ExoClock is an organized platform to maintain the timings for the Ariel targets until the launch day in 2028. It's an effort to make the best use of resources and bring everyone together. And because we believe that science is really a collaborative effort, we want to include as many people as possible in the ExoClock project, as the Ariel mission itself has many people as well. After all, every transit in our project is really an important effort, and every person can bring their own perspective and reach the final outcome. Now, ExoClock can be summarized with 3 keywords. So these are that ExoClock is inclusive, it is integrated, and is interactive. So it is inclusive because it includes people from different backgrounds and disciplines. People like professional astronomers, amateur astronomers, students from schools and universities, but also industry partners. It is integrated, and that means that we combine data coming from multiple sources, such as space, literature, but also ground networks. And finally, it is interactive, and that means that it is focused on personalized features, user-friendly tools. Feedback is given to the participants in the project, and we try to maintain as much as possible continuous user engagement. We will see each of these aspects in more detail now. So first of all, because ExoClock is an open and inclusive project, and we want to include also people from different backgrounds and different levels of experience, and at the same time, it is very important to maintain validity and consistency in all stages until the final product, the final results. We follow some strategies, and to achieve both scope of maintaining the validity and including many people. First of all, we share common protocols. So that includes observational guidelines, user-friendly tools, and a dedicated software for the data analysis part, which is open and accessible for everyone. All this material can be found on exoworldspies.com, which is a separate website. It's more from an educational perspective. And at the moment, all the material is provided at 5 different languages. So if you are also interested in participating on a different perspective and you want to help with translating in a different language, please contact us, and it will be great to share the material with more communities. Secondly, we perform the final interpretation of the data online, so we can validate the results always before they are getting published. And thirdly, the third strategy is that we organize training sessions and we provide feedback to participants in order to facilitate all the different levels of users. Regarding the second keyword of the nature for ExoClock, it's an integrated platform. So first of all, we use data coming from space. And that is very important for targets that are not accessible from the ground or for targets that are really challenging. Secondly, we use data coming from the literature, and that includes all the past, current, and future papers. And thirdly, we use data coming from ground networks. That includes the ExoClock network, of course, the Telescope Live network with Marco Rocchetto, and we have also synergy with a very well-known exoplanet transit database, ETD, and this is represented by Phil Walter. And finally, we also have a collaboration with the Exoplanet Watch program with Rob Zellem, who is focused on the US side and the NASA missions. Finally, and most importantly, every activity on ExoClock is organized through an interactive website. So participants can really register, can sign up in the website, and actually this is free and open to everyone. There is no required prerequisite or level of experience to sign up. And you can find the website at exoclock.space, just as it appears here. So you can become a member, and as soon you have signed up, we'll show you now what is the next process. So as soon you have created an account, you can click to My Profile, where it's shown now. You can add your telescopes to the platform. And then after this, you can actually include all the details related to your telescope, the observatory name, the latitude, the longitude, the model of the camera, and also some other information regarding your horizon. So if you have any obstacle like a tree or a building where you are, you can include that, and that will be taken into account. So the schedule will give you only the observable transits based on your details. Now, you can, once you have added your telescope, you can see that it appears also on the map, and you can check if it is correct, on the correct place. You can always edit the details as it is shown, or set as inactive the telescope if you don't use it anymore. The next step will be to check your schedule. So as soon as you have registered your telescopes too, you go to My Schedule, as it will now appear, and then you can see which planets are observable for every day or for later on. This is a list for all the transits that are observable at a specific time. And again, there are some fundamental details included, so you can check how many observations are so far in the database. Also, information about the star itself, the transit, and there will be the time that starts, the transit starts before, 1 hour always before, 1 hour after. With red, you can see if in some cases the target is not observable from the beginning, so you will see that this is marked always with red. So it's like paying attention. More information like the maximum counts that the observation will reach during the night, and information about the moon illumination. Now, you will also notice a very important feature, which is the prioritization system. And we have 4 priorities: the alert, the high, medium, and low. And this is actually really important because in this way, we can encourage you to go and observe at a specific target which needs more observations, or for some reason there is a higher intensity compared to another one. This is really also one of the features that allowed us to follow up observations on targets that were for some reason out of time, even if they were marked as low. And then, as soon as you have done your observation, then the next step is to analyze it and upload it. So let's see. More on how to conduct observation. Martin will talk more about that, and how to analyze it. Angelos will be focused on this part. So here it's really how to upload it on ExoClock. So you click to My Lab, upload observation as it's shown here. And you click the telescope, you choose a TXT file and the file that is your photometry. And then the planet, which is the target that you have observed, for example, Qatar 1b here, the time format, which is absolutely important, and because we're talking about timing, and you can see different formats here, so make sure it's the correct one. The timestamp, then the flux format, and finally, which filter you have used. We recommend the red one, but there are other options as well, as you can see. Finally, you will be asked to give the exposure time in seconds, the tetratic method that you have used, and there are two boxes, one for adding any co-observers if there were any, and also a comment section where you can add any information about the observation that you had. For example, the weather conditions, any things about the comparison stars, or anything else you would like to share with us. Then you click to upload observation, and now you will see the final result as it will appear in ExoClock. So this is the stage, which is a preliminary analysis. And there you have the option to really redo the analysis if you don't see an agreement with the predictions. So as you see, there is the prediction and your results, and the blue means that there is an agreement with the prediction. If there is a red color, that means that there is an inconsistency. And this is really your chance to redo the analysis and upload then the observation again. In any case, even if the text is on red, which means there is something wrong maybe, you can still upload the observation if you feel unsure, and we will send it back with feedback to you in order to correct it and then publish it. You can also delete observation in case you want so, and then you submit observation to ExoClock. This is the final result that will appear also in the website, in the database, and we will always, as I said before, validate the results before they are published for consistency reasons. Now, apart from these observed related features, we have also a separate tab, which is to share material with you, with the participants. So when you click here to database, sorry, to ExoClock, you will see there is a tab material. Here we share newsletters, monthly newsletters with different topics of discussion, questions, and we also organize Zoom meetings with the community in order to discuss several topics, give updates, and answer questions that participants might have. This is an excellent opportunity to connect with the community, and you can always revisit any information you forgot or you want to engage more. Very recently, we had also started our Slack channel. So this is also another way that participants can communicate together, and is a way to strengthen, again, this community spirit. Finally, ExoClock is also a service. So even if you're not a participant and registered, you will find our database where we share information about all the targets that Ariel will observe. And if you're interested in planning an observation, you can always visit this database and find information about the ephemeris, the star, the transit parameters, the limb darkening parameters, and you will also find the exoclock status. So here, as you see, for example, for the particular target, this is the OC diagram. So with the red points, you see the exoclock observations, and with the gray part is uncertainty, the prediction actually of the ephemeris, and the uncertainty it has through the years until the launch date, which is in 2029. And with blue, you see the area that we really want to achieve with exoclock. So we really want to have this as our uncertainty. And every time, either with confirmation or update of the ephemerides, we want to be inside this blue area. This is all open and accessible to everyone. So again, I want to mention that this is also for other purposes, apart from the Ariel mission, if you want to do another research project. Finally, you will find a tab with our team, which is all the time expanding. We are very happy for that. We have also national contacts, as you see here. And if you are from one of these countries or even another country and you don't see the national contact, you can contact us or your national contact, and we will be happy to assist you. Before reaching the end of this introduction to ExoClock, I would like to share some brief information about the current status and the first results. So we launched last year in EPSC, September 2019. So we are 1 year in operation. We have so far 170 participants, out of whom more of them actually are amateur astronomers. I'm very, very happy for that. More than 15 countries, as you see on the map as well. And so far there are 220 telescopes registered with the sizes ranging between 6 to 40 inches. So there are even very small telescopes contributing to the mission. There are 1,400 observations at least at the moment, and 175 targets have been observed out of the 370 that are at the moment in the mission reference sample. But this is all the time getting updated based on the new discoveries that we have. One of our highlights, and very recently we had our first ExoClock publication, and most of the co-authors that you see in this publication are amateur astronomers. And this is actually one of the most important things for us, that if there is an observer in the project, it becomes directly a co-author and equally participating in the project. We have confirmed the ephemerides of 59 targets, and we have refined the ephemerides of 28 targets, and there are more to come during the next years. And finally, apart from the ExoClock project and the contribution from the observational perspective, we are launching a separate campaign for our logo. So there have been different people that have been asking if there is a specific logo. At the moment, this is the logo we have, but if you're feeling really creative and inspired by this effort and you want to contribute from a different perspective, and you don't have an equipment, of course, you can always join from this perspective. So you can share with us your ideas by sending the logo at our email, exoclock.project@gmail.com. We have set as a deadline the 13th of November. And of course, either if you're a member, a separate team or a school team, we will be happy to receive your suggestions. But nothing comes without a prize. So we have a big prize for that, observing time with the telescope live. And we're very happy for this collaboration. And actually, Telescope Live is coordinated by Marco Rocchetto, who is also a very active member of our team. And he has kindly provided this prize. So it's really a nice opportunity if you want to get some observing time, either for ExoClock, and then you become also member of one of our publications, or for your own personal interest observations. To sum up, ExoClock is inclusive, interactive, and integrated, and we really try to combine as many features as possible and include as many people as possible. The main aim of the project is to monitor the ephemeridess of the Ariel targets, and since science is a collaborative effort, we strongly believe to everyone's perspective, every transit counts, is a unique opportunity to contribute to the mission, and it's a way that small telescopes can become useful. You can register at ExoClock directly if you want to start observing and start submitting your contributions, or you can start training at ExoWorld Spice, which is the separate website. And I want to mention that in this website, you will find also some available data which you can use actually to train. So you don't even need a telescope at the moment. If you have any questions, you can always contact us, and we will be very happy to have you in our project. Thank you. So, if there are any questions, please, I will keep them for the end. And now we can move to the next presentation, which is by an active participant in ExoClock, and the presentation is by Martin Crowe from the British Astronomical Association. So Martin, whenever you are ready, you can start.
Okay, you can hear me now, yes?
Perfect, yes.
Oh. Can you see my screen?
Perfect, yes, we can see it.
Okay, can you see my mouse? Does my mouse show up?
Yes, yes, we can.
Good, okay. Okay, right, so I'm Martin Crowe. I'm one of the amateur participants in the ExoClock Project, and I've been asked to give a brief overview of my experience, the equipment I use, and maybe get some of you others who aren't doing it interested in doing it. So I'm a member of the British Astronomical Association and Crayford Manor House Astronomical Society. And ever since I've been doing observational astronomy, I've always been interested in the science side of things. So photometry of variable stars, asteroids, and of course now exoplanets. And ExoClock didn't really, well, it only showed up on my radar late last year. And it's just been great. It's been really a good focus for my observing efforts, and great to be part of a team and a project with such a clear goal in mind. Now, I live in a place called Burnham-on-Crouch. It's quite a pretty part of the country. It's near the Essex coast and on the Dengie Marshes. And this light pollution map will show that the skies here aren't too bad by today's standards, and certainly better than where I used to live, that was over here in Dartford, where it was quite light polluted. But don't be put off, if you're thinking of doing it, by light pollution. A good friend of mine, Simon Dawes, is observing from Bexley Heath, which is under the sort of red area, and his results are fine. So don't be put off by that. Observatory. Well, I would definitely suggest that you need an observatory, or certainly a permanent setup if you're going to do this. It's certainly a good excuse to build your observatory if you haven't got one. Now I've got a domed telescope enclosure with a separate warm room. I like having a dome. It protects from, when you get those windy nights, I don't get any trouble with that. I don't get any vibration, and any stray light from those pesky security lights is generally blocked out. The warm room, I've got a PC in there with a couple of monitors, and I like 2 monitors because I can display all of my control software all at once. And one of the good things about that is that my dome isn't motorized, and I don't stay in there. So I go backwards and forwards every half an hour to move the dome, but I can look at the monitors and at a glance I can just see if everything's ticking over as it should. So I really like that. Equipment wise, well, there's nothing really special here. If you're an imager, you'll have all this gear already. But I've got 235mm diameter Schmidt-Cassegrain. It's native f10, but I always run it f6. I find that much better. It's got a carbon fibre tube, so that's really great for keeping focus. Camera-wise, I've got a Starlight SX694 mono CCD, some sort of moderate size sensor, but it's really good with this setup and gives me half a degree on the long axis, which is great when you're looking for target, or not target, sorry, check stars for the photometry. And also, I mean, received wisdom was that CCDs were what you needed, but CMOS sensors certainly seem to be doing a good job, and Simon is using a CMOS, and that looks great, his results. Pixel size is quite small these days, but half second arc second resolution. Filter wheel, I've got Astrodon photometric filters in here, and if you are doing the project, it is good if you can use a Cousins R filter, because it allows for continuity with other people's observations. But as Anastasia said, it's not necessary that you have that. You can use a red filter or no filter, but as long as the team knows. And I'll just guide the whole lot with a little Lodestar, which is a nice sensitive camera. Software wise, now again, if you are imaging, you've probably got software already that's going to do all or almost everything that you need. You have that already. But if there is any bits that are missing, then there's freeware out there. And all of my software is freeware. Maybe I'm a cheapskate, but it's there, you know. So I use C2A Planetarium software. It connects nicely to the telescope via ASCOM. The image capture software is freeware by a BAA member written by Grant Privet. That's been great for me. It does exactly what I want. And he's even done modifications to it based on suggestions that I've given to him. And that's for all sort of Starlight cameras. Guiding, I use PhD2. That's, well, everyone uses, well, not everyone, but a lot of people use that, and it's intuitive and it does what I want it to do. Filter wheel software, I just use the manufacturer's control software. All Sky Plate Solver. Now this is really good. I've only been using it this year, but it's just great. If I lose track, or my mount lose track of where it is on the sky, all I need to do is take an image anywhere on the sky. It doesn't matter. Let it plate solve it, and then it will sync the mount. And within 2-3 minutes max, I'm back in the game. It's just great. No more 3-star alignments or anything. Astro Image J. Now this software I would normally use for photometry for other targets such as variable stars or asteroids. But in this context, I use it to check my images when I'm setting up and as I'm going along. But when I'm setting up, it's so I get the exposure right, and also that the target's where I want it. And the target star doesn't always want to be in the middle of the image. It might want to be off to one side, depending where the check stars are. And of course, there's the HOPS software, which is the bespoke software that comes with the project, and that's just great. And if you've never done photometry before, fear not, because it will just do it all for you. And there's good support, and there's improvements to it all the time. It's always doing extra stuff. Very, very good. Makes life very easy. Now, my process probably is not going to be any different to anyone else who's got an observatory and does imaging or whatever. But for me, I find routine is key, because if you're going to do this, you're going to be tied up for about 5 hours. And it's so annoying if you get to the end of it and you find that there's some little thing that you forgot to do. It's maddening. And so I do everything. I have this set sequence. So it's power up, open up, connect the software to the hardware, and I always do it in this same sequence so I don't forget anything, and set the parameters that I want. Switch on the dew bands, that's always useful. And then I'll check my schedule, which I'll have already looked at, and have a target star, load up my RA and deck into the planetarium software so I can see if it is going to be obstructed at all. It's not normally, it's usually pretty good. And I'm ready to go, really. This bit I've just spoken about, it's about the astrometry and syncing them out. Checking your PC clock's a good idea, especially with this project, seeing as it's all about timing. So that's very, very important. Slewing to the target and taking test images, I mentioned that briefly just now with AIJ. And checking the focus, and I'll come back to that in a second. And then lastly, I'll set the file name and I'm off. And I follow that routine and never have any problems. Anastasia spoke about my schedule, and so this is one for my location, and as she said, it's tailored to your setup, and clearly the traffic light system they have for the priorities is, you know, the highest ones are most important, and working down to the lowest ones. Now I have to admit, when I look at this, because I have to go to work the next day, the first column that I look at is actually the right-hand column, the last one. When does it finish? Because I've got to stay to the bitter end because my observatory is not fully automated. That's very important to me. And so, just for instance, with this particular one, the one that should have been done really was the medium priority target. But in the end, it was a bit too late for me, you see. So I, in the end, picked this one, WASP 58. It wasn't the earliest one by any means, but it was sort of acceptable, and it only had one recent observation, so I felt that was the one to do, and it would back up that observation either way. Checking the images before I start and while I go along, I use AIJ, and of course there's other software that will do the same thing. It allows me to go to the stars that I'm interested in and see what their peak pixel value is. And that's obviously important, and it's starting to determine what exposure to use. But I also have to do this in conjunction with the profile of the star, which will tell me what the full width half maximum is. And in this case, it was just under 4.5 pixels. And I know from my setup that that is pretty tight focus. And there's a bit of a problem with that for my setup with those small pixels, that 4.5 micron pixels. What happens is that between exposures, if it's too sharp, this value can change quite widely. And so what you don't want is to suddenly find in a few exposures time, it's ripped up to be in the non-linear part of the camera's response. And so normally I'll just slightly defocus so that it's about 6 or 7 pixels, and that smooths that out. Now, HOPS, when you're doing the photometry within the HOPS software, it will give you suggestions for check stars. These are the yellow circled ones. But the only thing is it doesn't take into account, or not currently anyway, it doesn't take into account the star's colours or whether they're variable or not. And so the method that I've been employing, and there are other methods that other people use, but this one, I go to the AAVSO website, and I type the star in, pick a star, so WASP 10 in this instance, and create a finder chart. And it will give you a chart like this with the target star and then check stars around it, which you know aren't going to be variable. And there's a table that comes with it, which has the B-V for those stars so that you can see what their colours are. And in this particular instance, I've picked these 4 here because they were relatively similar in colour. And 3 of them are the same as some of the stars picked by HOPS, and one of them wasn't. But of course, whether these other ones were varying or what colour they were, I've no idea. So this is how I based it. Keeping an observing log is extremely important. Just the date, this is always the evening date, what the weather's doing, if the weather changed at night and what time it did it, the equipment I've used and any settings or the settings, the target, the RA and deck, and that's really useful if you have to go back for some reason, you haven't got to go looking it up. And also the check stars that we used in HOPS to do the photometry, because again, if it does come back for any reason, you've got all this information to hand, you've got to go searching it out again. And when I uploaded it to the ExoClock project so that I know I've done it. I'm not going to talk about HOPS at all because that's Angelos's thing he's going to be doing in a minute, I believe. Just to say that light frames and calibration frames, once you've got those, the HOPS is going to do the rest for you, and hopefully you'll come out with a lovely transit light curve which will be put into the to the project archive. And I don't know if I've got time for this very quickly. Don't forget, you can data mine your own images in that you're staring at a piece of sky for 5 hours, and often there's other variable stars in the same field, and so you can measure those as well and send those off to the archives of the BAA VSS and the AA VSO. So that's me done. Finished. Anyone out there?
Yes, so thank you very much, Martin, for describing the whole process. I think we really encourage more participants, and I think it's really useful. So if anyone, I think we have just room for one question, quick question. So, which is answered, how do you use AstroImage to check saturation and required exposure time? You mentioned this already, there is no reason to respond to that. Someone says, Martin, this is so cool. It's so interesting to learn the methodology and process of the astronomer. Okay, very envious of your setup. Right, okay, no questions so far. Let's see if at the end we have an extra question. I think we can move to Angelos' talk. Thank you again, Martin. And the next and final talk is which is more of a demonstration by Angelos, who will show more on the HOPS software. Angelos, let's see if you're ready. When you're ready, you can start.
Hello, everyone. Can you see my screen? Yeah.
Yes, yes.
Good. Right. So thanks to all who are still waiting. It's the last presentation. Actually, it's not really a presentation. It's a quick demonstration on the tools that we have developed, especially the whole photometric software HOPS. It is a work which started many years ago, and actually in collaboration with amateur astronomers who gave us a lot of feedback on different features and what they would like to see, and the level actually of the difficulties that they had to go through. So all in all, to support the observers, especially the not so experienced ones, at least in exoplanet observations, we offered together within the ExoClock project the HOPS software. So if you look at the project web page, and then you go down, there is Start Observing, where we give some information about how to observe and also how to analyze the data and where to find the software. So if you click on this, you will be sent to the ExoClock page that Anastasia showed to download the software and the manual on how to use it. Thanks to our participants, we have translated this material to different languages, so you can find it in your own language if available at the moment. So I will start with a quick demonstration. Understand it's a bit technical, so since the meeting is recorded, I think it will be useful if you can come back and watch it again if you want later on. So On the webpage, you will find information on how to install it. Usually it's a smooth process, but if not, just send me an email. Usually there are no problems, but once everything is installed, you will see just an executable here on your desktop. And by running, you should start the analysis process. So here it comes, and here's my email, by the way, in case you have any questions. So first thing is to choose a directory where you have saved your data. I have saved all this data here from an old observation. I think it's a good tactic to save all the observations with the names, let's say, of the target, like Qatar 1b in this case, and then use like bias, dark, and flat for your reduction frames. Just to remind that it is very, very important to include these reduction frames in your analysis. But if you're using already reduced data, you can just not include reduction frames and continue with the rest of the analysis. So I'll choose my folder here, desktop, and okay, choose. And now, as I said, the name identifier in my case was Qatar. This indicates all the field of view images. And then the bias, dark, flat, these are the names that I usually use, but someone could use something else. Here it tells you if the files have been found. If not, you can have a look at which files are in your directory. Like here, it's a complete list, set Qatar 1b, and then bias, dark, flat to be analyzed. Then the code usually detects some of the important information that are needed, especially for timing and for the target, like array and deck of the target. If it is not correct, or if you want to include something else, you can, of course, import this manually. But usually, in most cases, telescopes save these numbers in the file's header. Then we have the exposure time, the observation date, observation time, and the timestamp, which tells you whether the time corresponds to the beginning of the observation or the middle of the observation. In case you do not find these keywords, like here they are found, you can have a look at your file header and check, for example, here is the exposure. It was 120 seconds. If everything looks fine, you can just start run reduction. Here the code will create the master bias, master dark, and master flat using median over the files that have been supplied by you in this case, and at the same time calculate different statistics about the images, like the sky background levels and some noise that you like, something like the SNR of your observation to help later on. After reduction is completed, you can have here a curve showing the time and the sky. Here you can see which frames may be very bright. For example, if there is satellite passing or if the sun is rising, you will see that the sky background is quite high up. You can reject if you want some images, like you can inspect, of course, the images, and if you don't like them, you can just do as said here, double right click to exclude the point or not. Here, there is nothing really strange going on. There's some fluctuations, usually due to humidity. And then you can run your alignment. During the alignment, the code is detecting the star pattern in your observations and then detects how the stars are moving through your observation. This is done by using some polar coordinates of your field of view. Of course, if your guiding is very good, then this is practically not necessary. But there are cases where we used to have meridian flips during the observation. In this case, the field of view is flipped. The code does not really find anything, but asks us if this is a destroyed frame. No, not in this case. And it will start looking around for the stellar pattern that it was used earlier on. In this case, we'd like to avoid the problem of pair flipping and detecting the stars. So here it is. Usually it's quite fast, but depends also on your computer. Once everything is done, you will see the windows with the photometry. So here is your field of view. With red, you can see the area that was continuously monitored throughout your observation. As you saw, the image was moving and then flipped. So these areas were not monitored throughout the whole observation. So only targets within the red box will be you will be able to select only these stars. Now, in this case, as I said, we were observing Qatar 1b. If you don't know where the star is, you can go to the ExoClock webpage and look for Qatar 1b as Anastasia. So there are information about the field of view for its target in our target list. And in this case, I remember by heart because I was observing this planet for long. Here is Qatar 1b. I select my target and double click on it. You can see the aperture. In this case, it's a bit small because the guiding was not perfect and the star is not symmetric. I will just increase it a bit to include most of the star. And then the code gives me some suggestions about comparison stars. Because there was a pair flip, I usually try to select stars that are symmetrically distributed around my target. So in this case, I will pick this, which is, I know it's a nice target. As Martin very well showed, this is not always the best case, because if this star is a variable or it has a completely different color compared to our target, this will not be very good. So I strongly suggest going through some databases, like there is here a direct link to Simbat for this field of view to check for stars, but also, as Martin saw, the AAVSO website is a very efficient way of finding the variable stars. So I will use this one, and then I will check for comparison too. It's better if you have two comparisons. And as I said, I use them symmetrically, usually when I have pair where I have a meridian flip, because there are some offsets that I want to avoid. Yeah, there's no reason to explain more here. I don't have much time. And then you can click Run Photometry. You can see how the target is changing. You can see that here the shape is changing through the observation. As I said, guiding is not perfect all the time. So you can check that the star stays always within the aperture. It happens that during the observation, the PSF of the star changes, in some cases a lot. So you can investigate here whether the star becomes too big, for example, and goes out of your aperture. In this case, it was actually the opposite. The star became a bit smaller, so the aperture probably could be a bit smaller. At the end, you will see the final result. And this is what everyone, I guess, is waiting for at the end of the observation, especially with a transit, to see a transit. So here's a transit light curve from our target, and the other plots show the light curves of the comparison stars. Here you can see an offset, a different offset for the two targets. This is because of the pair flip or the meridian flip, as I said. You can see two light curves. One is called aperture because it's performed by aperture photometry, and the other one is PSF because the code is performing a PSF photometry where a 2D Gaussian is fitted on the target's profile to extract the flux. So transit is here, everything is ready. You can move on to the final stage. So at this point, the result can be uploaded to the ExoClock website. You don't need to do anything on your computer. And as you saw, I spent only a couple of minutes. Now, if you're using HOPS for different purposes, or if you want to test your result on your computer before uploading, as Anastasia showed the uploading earlier, you can try to do the fitting on your laptop. So here's a fitting window where you can choose between the two light curves, like the aperture or the PSF, which is called Gauss here. Then you choose the filter observation, in this case was red, some information that are usually shared within the fits header, but most importantly, the information about the planet. For all the planets in the ExoClock database, we have integrated the parameters inside the code. So the code detected that this is Qatar 1b and pulled all the parameters from actually, they are the same as on the website. They're not pulled like live. You don't need internet connection here, but they are displayed here, and you can see your light curve and the fitted model. So the red is the fitted model, the blue is the expected model, since they are close, it seems that the result is quite good. You can see a first snapshot of the OCDI of the observed minus calculated. So there is a small shift of 3 minutes here. And you can see some diagnostics about the goodness of fit. So the standard deviation of the residuals and the autocorrelation, which if these two numbers are very high, it means that something went wrong with observation, and maybe you use the variable comparison star, for example. Now I will not run the fitting because it takes more than 5 minutes usually. So I will just close it. I have a fitting result here, where you can find, well, the most important one is the detrended model, where you can see the final plot. Here you see the OC diagram and the final results of the of your fitting. And well, again, as I said, the standard deviation of the residuals, but you can upload even earlier on in your analysis. Here you can see a representation of the final result. And yep, that's all for me. As I said, it's quite technical, so I'm happy to answer any questions, but if it is too detailed, maybe we can you can send me an email if you want. Otherwise, we will have the Q&A session now in the next few minutes. So I will stop the presentation.
Okay. So thank you very much, Angelos, for the nice presentation and demonstration. We have a few questions. Now it's your time to respond to different parts of the presentations. We have one question that is regarding Ariel. So maybe Giovanna, if you're around, the question is it known which exoplanets have atmospheres before Ariel launch? And if so, will planets with solid surfaces and no atmospheres be excluded, or is it expected that a certain percentage will not yield the results?
It's an excellent question. For a fraction of the planets that Ariel will observe, we will know something about those planets. In particular, already today, we have a number of exoplanets for which we have Hubble or Spitzer observation that tell us something about the atmosphere of these planets, although the information is still very preliminary and not very conclusive. But of course, the question whether or not a planet has an atmosphere is actually an extremely important one, a question that we really would love to be able to answer. And so there were some observations done with Spitzer recently that showed that in principle, if you have a look at a phase curve for an exoplanet, and if this planet doesn't have an atmosphere, you would see a pretty large thermal gradient at different phases. And so in principle, we think we have a way also to find out, at least for a small fraction of planets, whether there is no atmosphere at all. And so again, this would be a fantastic result, because knowing whether or not planets can retain an atmosphere is one of the key open questions, especially for the small one.
Great. Thank you, Giovanna. Another question that is similar, for Ariel, is if there is any perspective of a mutual collaboration with Plato.
Yes, of course. So we're already discussing this. Plato hasn't published yet the list of stars that will, well, actually not list of stars, because of course they're searching for planets, but the area, the confirmed area of sky they will look at. But it is foreseen that many of the results from Plato in terms of new planets being discovered will be incorporated in the target list. So of course, so far we have been focusing mainly on TESS, because TESS is flying, and so we start already to have some results. But definitely Ariel will collect all great results from any observatories, and clearly Plato being a dedicated observatory to find planets that are transiting will be definitely one.
Great, I hope this answers the question. Thank you, Giovanna. There is a question regarding the data analysis part. So Angelos, is there a way to enlarge the entire light curve window in HOPS to select outliers? This is one question.
Sorry, where is the question? I cannot really read it on the chat.
So if there is a way to enlarge the entire light curve window in HOPS to select the outliers. Right.
You can select the outlier. There is an option for anyway, it was called the scatter limit. So you can increase, you can actually increase the threshold and exclude automatically outliers, but not by hand. Yeah.
I hope this was like heard, because I didn't really listen the first part, but another question is by Philip. May I theoretically use HOPS to detrend my data and then combine data to make one precise observation using several telescopes?
In theory, yes, but in practice, it is better if you do the detrending at the same time as the modeling. So I'm not 100% sure this would work. I would suggest doing, I mean, HOPS cannot really handle at the moment multiple observations. So you will need some other software or custom script to do the analysis, because I would prefer to do it simultaneously. In theory, yes, you can do this.
And another question is, can you move the aperture circle so that the whole star fits in? And does it really matter?
Well, the star should be within the aperture. So the aperture should not be much larger than the star, but not smaller than the star. It should be just to include the whole star. This way we achieve better signal to noise.
And then we have a question for Martin. So I'm in North Kent on the other side of Thames estuary from you. How many days per year can you observe?
Blimey. A good old friend once said, the thing with astronomy, it doesn't interfere with the drinking time too much. It's very difficult to answer, because you go through periods when you can have really sort of like, you have a week of it almost, and you want it to be cloudy. But I don't know, I suppose, potentially, I suppose you could say, I don't know, 40 to 50 nights, I would, that's a real sort of guesstimate, you know. And of course, yeah, it's a very difficult one to answer. But I mean, whatever I get, if you're in North Kent, you should be getting similar. I mean, I'm slightly up the coast just a little bit, and sometimes it can be better here out near the marshes than a bit further inland. But also, the contrary is sometimes it can be reversed, and you can be cloudy here and it's clear the other way around. So it's a bit swings and roundabouts. Very difficult question to answer, I'm afraid.
Okay, thank you. And I think we have another question for, let's see, for Martin, no? Okay.
Someone has asked how to join the Slack channel.
Yes. Yes, we can, please send us an email at ExoClock, and we will send you an invitation. To Angelos, is it planned to include the astrometric solution in HOPS to get the right ascension and the declination on the field of view image?
Good point. I will consider it included, not at the moment.
Are there observations in 2020 as important as later observations nearer launch? Okay.
Well, the important thing is to have observations very far from each other to get a good ephemeris. But of course, the closer we get to the mission, the most important they get. The problem is that if a target has at the moment very large uncertainty, and you try observe it in 7 years, you may not know where the transit is. So it's important to start following them up from now until the launch of the mission. Not every day, not every month, but let's say like once per year.
Good. Then we have a question regarding, I think it's for me, is the pre-launch transit survey completed before Ariel's launch, or the database can be updated, including additional targets after the launch and during Ariel operation? So definitely we will continue to have the database and ExoClock during the Ariel operation, because Ariel will not observe all the targets in one way. So until it ends, definitely, and then we will continue. We plan to continue to have the service for the ephemerides as well. I think one more question, or yes. So, are you planning to have any practical labs for amateur astronomers on Telescope Live or other robotic telescopes to observe the transits and apply photometry tools? Very interesting and a nice idea. And definitely we can, yes, consider this too. So as soon as we are in
I think I saw Marco at some point.
With Marco, yes.
If he can answer.
Of course.
But I'm not sure he's still here.
If he's still around, yes. But I think that was definitely one of the ideas we had with Telescope Live too. I don't see him around, so...
We'll keep the question.
Yes, we will definitely keep the question. If you don't have any other questions, or do you think that everything was answered? Definitely, if you have more questions, you can send us at ExoClock, either regarding the mission or the project. Please tell me if there is a question that was not answered. Then we can gradually end up the meeting. Before we end up the meeting, I would like to thank a lot the speakers for joining this important session. And of course, all the participants of today's session. I would like to say that it is really important for us to have all this collaboration with the amateur community. And please join us. We will be happy to have you in the process. And finally, I would like to thank Europlanet for this opportunity. And the meeting will be available for later on. So you can find it in the EPSC website if you want to watch it again and share it with other communities. And just to finish up saying that send us your suggestions for the logo. We'll be happy to have your ideas. And yeah, one more time, thanks to everyone and our speakers. It was excellent to have you all here.
Thank you for the invitation. Thanks, Anastasia and Angelos.
Anastasia, thanks to you.
Thank you, everyone.
Yes, thank you. Yeah.
Bye.
Thank you, Martin, Athanasia, Giovanna, Angelos, everyone.
No worries.
Thank you. Goodbye.
Bye-bye.
Bye, everyone.
Goodbye.